In the second video for lesson 1.1 and 1.2, we're going to look at this figure and we're going to be using notation. And again, as we're working on this, I will be adding to your vocabulary list and making sure I clarify anything. But one thing I did want to mention, if there's any questions that you have as we're working through this, I would make some notes in your notebook or put out on a sticky note or something like that. And that way when we meet in class or we meet for our time together as a group, our in-person time or our Zoom time, you can then ask those clarifying questions. So let's get into it. We have a figure over here, which you can see, and there's a lot of things happening, and I'm just going to go through what we're being asked for and then continue to identify what's happening. The first thing is we are asking for 4 points. Now remember, there's an infinite number of points when we look at a figure, but we only have 4 named points, and that's really what we're after right now. When we name a point, we name it with a capital letter, and it's a printed letter, and a point, remember, is a location in space with no size or shape. And so our 4 points are T, E, A, and M. And as I write them, I'm just going to use my capital printed letters and put commas in between. The next thing we're looking for is a line. A line goes infinitely in 2 directions, and there's an infinite number of points on a line, but we always say we need 2 points to determine a line. And what that means is if I have just 1 point, there's an infinite number of lines that can be drawn through that 1 point. But as soon as I have 2 points and I consider the line in between them, I have determined the line. If I look at my figure over here, there's only 1 line. And that's again because I'm looking for those arrows going infinitely in both directions. There are again an infinite number of lines in a figure, but when I'm identifying terms in a figure, I just want to assume what is there. When I go to name this line, I have to pick 2 of the points on the line. In this case, let me pick point T and E. And then I put my baby line over top of it to identify it as a line. I could have also written this as ET. You can write the points in any order, or you could have also called it line TA, line ET, any one of those iterations. You only use 2 points and you just draw those little arrows. The next thing is we're asking for a plane. So this figure is all on the same plane. In the plane, right, it's like a flat surface. Sometimes we draw like a parallelogram around it to determine that it's a plane. The reason why I know that I only have 1 plane here is because I don't have like 2 parallelograms in the picture. If I were to draw 2 planes, I would maybe draw something like this as my first plane, and then something like this as my second plane. And I would have like the different sort of intersections kind of drawn out as dashed lines. And that's how you can tell if something is in more than 1 plane. In a plane, we name it with 3 non-collinear points. Again, we need 3 points to determine a plane. We need 2 points to determine a line and 3 non-collinear points to determine a plane. So what do I mean by collinear? Again, being collinear means being on the same line. In this case, points T, E, and A are collinear, so I could not call this plane TEA or TAE. There's an infinite number of planes running through 3 collinear points. So what I would have to do is choose any 2 of the points that are collinear, because 2 points are always going to be collinear, no matter what. And then a third point. So let's say I choose point T and E. And then my third point could be point M. So I could call this plane TEM. I could choose EA and M. I could use MA and E, something of that iteration. If I can also call a plane by a cursive script capital letter if I have more than 1 plane in the figure. We are looking in number D for 3 line segments. So when we look for line segments, we're thinking about the 2 endpoints. And again, a line segment has the 2 endpoints and all the points in between. We have more than 3 line segments in this figure, so I'm actually going to identify them all for you. So our first line segment is line segment TE. Again, when I name a line segment, I pick the 2 endpoints. I put a baby line segment over top. Since there are no infinite, it doesn't go on infinitely, I don't put any arrows. Just like a line, I can reverse the order of the endpoint. So I could have called this line segment ET as well. I have line segment EA. I have line segment AM. I have line segment EM. Segment TM. And believe it or not, there's also one more segment. It's segment TA right up here. So there are 6 line segments in this figure. Our fifth thing that we're looking for are 2 rays. So again, there's more than 2 rays in this picture. A ray goes infinitely in one direction. And as we name a ray, we always name it by its endpoint. And then we go ahead and then pick one point that extends infinitely in the direction we're going with. And I'm going to detail that out in a second. All right, let's talk about the details of a ray here. So for example, let's say I want to consider a ray that starts at point T and goes to the right. Okay, so in this case, think of this. This is the ray I'm talking about. Starts at point T. My endpoint is T, so I'm going to put that first. Now, I could actually call this ray TE, or I could also call it ray TA. And that's because both A and E lie to the right of point T. They're in the same direction as the ray that I'm going in, and I can just go ahead and write that ray like that. I don't use 3 points. Again, I just use 2 points. However, let's consider the ray that starts at E and goes toward A. Here's point E and here's point A. This is not the same ray because the endpoint is different. You can see there are some overlapping right between the blue and the purple, but they're not the same ray. And that's, again, they're going in the same direction. They're part of the same line, but they're not the same ray because they have a different endpoint. Similarly, let's say I think about a ray that starts at E and goes toward T. So that is not the same ray as ray AE, because even though they have the same start point, they're going in a different direction. So that is a completely different ray, ray ET. So again, when you're considering thinking about rays and how to name them, you want to think about where you're starting and which direction you're going in. We also want to make sure, again, that the direction is correct. So if I'm talking about ray TA, just going back to ray TA, I can't call it ray ET, and I don't want to point the arrow from E to T because that would indicate a different ray. Let's go through some other rays that we see in this picture. We also have ray AT, which I could also call ray AE. And then I have one more ray, and that is ray TM. It starts at T and goes toward M, again, because I have that arrow. There are, of course, again, an infinite number of rays, but in terms of like naming them, I really just want to think about what is in the picture itself. So for example, there is a ray that starts at A and goes in this direction, but I don't have a second point to name it. So I'm not going to name it in this case. I can't just name a ray by one endpoint because I don't know where it's going. I also don't want to consider a ray between A and M in this picture, for example, because there's no arrow going out. Even though there is, technically, in the actual figure itself, I don't see it there. So we're just not naming things that we don't see in the picture. In F, we're looking for a pair of congruent segments. So congruence means same size and shape. When we look at congruent segments, we're looking for tick marks. And we're looking for the same number of tick marks. So I see one tick mark between T and E, so segment TE, is congruent to segment EA, which also has the same number of tick marks. When I'm talking about congruence, I'm talking about the entire thing. I'm not just talking about the measure. And so I do want to make sure I name them as segments. And the symbol for congruence is an equal sign with a squiggle above it. So numbers and measures are equal. Segments, figures, angles, shapes are congruent. When we have congruent segments, we can find the midpoint as long as they are collinear, okay? If we can have congruent segments that aren't collinear, in this case they are. And so when we're looking, segment TA is divided into two equal segments, segment TE and segment EA, two congruent segments, where point E is the midpoint, and therefore we're calling point E the midpoint. I'm naming it as a point, so I just use that uppercase capital letter. And our final vocab word here is adjacent angles. So adjacent angles share a side and a vertex, but no overlapping point. And I can talk about adjacent angles a little bit more using the first figure as well. So adjacent angles are side by side. And again, we have a lot of angles in this figure, and we've already talked a little bit about naming angles in video 1. So let's consider angle TAE, which is right here, angle TAE. So again, I named the T, I named the vertex E, and then I named the M. I always put the vertex in the middle. That is adjacent or shares a side with angle AEM. And you can see that they share vertex E and they share ray EM. Okay? It is not, for example, adjacent to angle ETM. So here's angle ETM. Angle ETM is here. Angle TEM is here. Now they do share a side, right? They share side ET, but they don't share a vertex. One of them has vertex T, one of them has vertex E. So they do not share that piece. Therefore, they are not considered adjacent. One other piece I want to acknowledge is the idea of what we call overlapping angles. Now that was not in the definition, but I'm going to talk about it here. So let's consider angle TMA. So we can see this angle here. And this is what we say when we say adjacent angles do not share interior point. If I consider angle EMA, which is this angle right here, you can see these are the interior points. It shares the vertex with angle TMA, and it shares side MA, right, MA. But it also shares interior points because if I were to kind of color the interior of angle TMA, I can see that it is overlapping with that blue angle. So those are considered overlapping angles as opposed to adjacent angles. Again, if I was considering an adjacent angle with angle EMA, I would pick angle EMT. Those are adjacent. So I hope that helps clarify. This is the end of this video, and we will continue on with sketching in